Hi, this is Mike Lopez, and in this video we're going to be looking at a series RL circuit, and in particular the exponential growth and decay properties of this particular circuit. Okay, let's start off with the battery and call it the supply voltage Vs. We go through a switch. Once that's closed, our little experiment starts. Here's our resistor, and here's our inductor or coil, if you will. Okay, connect it back to the battery, and what we're interested in is the current flowing through this series circuit, call it I, and the voltage across the inductor, let's call it VL. Okay, and that should not be capital VL, it should be curly VL, because it's instantaneous voltage, of course. Okay, let's draw some axes in. I'd like to draw some analysis for the current. So current I on the vertical, here's the origin, here's time, and what we're hoping to see is some exponential growth in the current, looking like this, and that should reach a maximum asymptotically, as it's known, or plateau if you like, and that maximum value will be given by the supply voltage divided by the resistor value. So, you know, the resistor inhibits the current in the circuit. And indeed, this is some exponential growth properties going on. Let's have a look at another graph. This time, we're going to check out the inductor voltage VL, and what we expect to see with VL is some exponential decay. Okay, and that maximum value will be the supply voltage Vs. But again, there's exponential decay. So in this RL circuit, yes, we have some growth and decay depending on which parameter you're picking on, and the same was in the previous video for the RC circuit. But what you'll notice about the RL circuit, stick an L in there, what you'll notice about the RL circuit is the graphs tend to flip over, so they're exact opposite of the graphs for the RC circuit, which is quite curious. So check out the previous video and confirm that for yourself. What I would then like to do is jot down some formulae for these functions here. So the current is the supply voltage Vs over R times 1 minus e to the minus RT over L, and the voltage on the inductor is given by the supply voltage times e to the minus RT over L. Okay, and I'm particularly interested in this function here for current, and what I would like to do is find for L. In other words, I would like something that says L equals blah blah blah. Okay, just see if we can scroll down a bit and have a look at some possibilities. Well, we've got R here. That needs to be moved out of the way to the left. So does the Vs. Maybe we could do that first. So we'll multiply both sides by R. That will effectively move R on a diagonal. If we also divide both sides by Vs, then the Vs's will cancel on the right, and Vs will appear on the bottom left. Okay, so what we'll effectively have then is, keeping this colour, we're going to have I times R over Vs equals 1 minus e to the minus RT over L. Okay, and remember what the target is. Well, of course, the target is this L here. Okay, I'm trying to find for L. So what I also want to notice, change colours again, so wrap a cloud around this whole animal, and no, that's not a good idea. Let me just Control Z that one out. We'll wrap a cloud around this term here, and we move that over to the left, and we'll do the same with this one. I'm going to move that over to the right. Okay, so change colors again. So say therefore e to the minus RT over L equals 1 minus IR over VS. Okay, and then maybe it's a good idea to hit both sides of this expression with a log e. Reason being, it will obliterate that e to the whatever there. Okay, so that power will be what you see on the left hand side, which is quite good, because that's going to allow us to easily release L, and that's our target. Okay, so I'm going to then say, let me switch to red maybe. So therefore log the base e of e to the minus RT over L is log the base e of 1 minus IR over VS. Close that bracket. Okay, it's definitely a 1. Looks like something else. All right, and scroll down a little bit, and then we're looking for these two things here obliterate each other, and that just leaves me with minus RT over L on the left, which is quite cool. Minus RT over L equals log the base e of 1 minus IR over VS, and close that bracket. Okay, it's looking good. Now remember what we're after. Up here we're after this thing, L. So here's L on the bottom. Maybe to isolate L we need to move it across on that diagonal and cover hold of the whole of this thing and move that on the opposite diagonal, and then flip it round, change left for right, okay, which is the same thing. So that is then going to leave us with, finally, L equals minus RT all over log base e of 1 minus IR over VS. Okay, and there you have it. Okay, and what we're seeing here is an RL circuit, series circuit of course, in the microcap simulator. We open up the transient analysis limits, we set the range that we want on X and Y, we also set the time range, the maximum time step, a few other parameters, we hit run, and something very familiar in terms of exponential decay transpires.